Good evening, ladies and gentlemen. Okay, so a lot of this work, I say I'm in transit, but this was done at the University of Malaysia, Sabah, North Borneo. So what we're going to talk about is a little bit some work I've been thinking about and published a few years ago on what are the implicit assumptions behind the blue carbon model. And that takes a lot of contemplation. And it also is, these were ideas which I had, but we had to then go on and see how important these particular components are. So today we're going to talk a little about not so much the storage assumptions which we've been looking at, but the actual rates of sequestration. So if we just go to this very familiar, I don't know why I'm showing this because we've had these type of slides all the time, but in our research we augmented the blue carbon model a little bit. This is the conceptual model which everyone's more familiar with. Stuff comes in from mangroves and from maybe the land. It's trapped by the seagrass, it's sedimented, allochthonous production or litter and so forth, algae, seagrass and all sorts of things. Gets also trapped by the system itself. But also what we've done is augmented the model by adding another component to it called black carbon, which is a concept of allochthonous recalcitrants, which I'll talk about in another minute. And then usually we got the consideration which has not been talked about so much in this conference, calcium carbonate formation from epiphytes or shells, or even discovered that thalassia produces its own carbonates in the carbon concentrating mechanism, and the release of CO2, which may or may not happen if it's not recycled, and of course the net CO2 sequestration, followed by burial, loss to maybe the deep oceans, which we have to take into account because it is a form of external sequestration maybe. And then we've a bit of DOC, we're not too sure what happens to it, whether it's degraded or where it goes. And then finally, which we had talked about in the first session, some of it's retrapped back into adjacent mangroves and so forth. But with the black carbon, what I want to say about it is that traditional biogeochemical approaches are looked at mass balances, more or less. What's in, what's out, what's remaining. But what the goal of a lot of this science is to look at its surface in the mitigation of climate change. And for that, without that storage and sequestration itself is a sterile concept unless you put context on it. And when you put context on it, certain things emerge, questions. And one of them is the concept of allochthonous recalcitrants. That means if something is produced outside the ecosystem and already stable, like black carbon, which is ubiquitous, the world's on fire, pollution and so forth, then it gets washed into the system. It no longer needs the protection of burial to stop it from mineralizing back to CO2. As a consequence, if we're including it in a total organic carbon analysis, we are overestimating the service for mitigation. And in doing so, if we do go to carbon credits, then you will overestimate the capacity in the mitigation of CO2 release of the system and allow the company or whoever to emit more CO2 than the system can handle in the mitigation. And that will lead to increased greenhouse gas emissions. So it's not a good story, but it's an important story to take into account. The question there's a paper on that we published in February, which more or less summarizes and gives data to see how important this component is. Since then, we've added a little bit more data to it. The original data set in the paper, we did some regressions and so forth, and we predicted what the open water systems are, not the hot spots of the estuaries where it was done. And this is the area here, just to give you an idea. But when we went out the outside into the more open coastal systems, there's actually our predictions were wrong. There was more black carbon as a percentage of the total than actually we predicted within the estuary. So it's an important component to remove, and it's a bias of over maybe 40% or so, which on the service to the mitigation of climate change, you don't take that into account. It's also highly variable. But our assumption, of course, is that doesn't degrade over time. So we're testing my own assumptions before anyone has a chance to challenge my assumptions, because it's fairly early work. So as part of this study, one of the other assumptions is for example, by just Sebrien, it's a fantastic name, is that when we do get burial, after about a couple of years, more or less the carbon is stable. So then people have then measured the rate of sequestration by measuring the rate of sedimentation, multiplied by the organic content, and bulk density and so forth, and get the rate of sequestration. However, from bare sediments, we know more or less, just the model, the animation there, is that it actually does degrade. And before it was time independent, but because it's a continuous function, we have to put a nail, a time on when we want to actually say how long it takes to degrade. In climate change, it's generally regarded as centennial changes. Within the model as well, of course, people assume that the inorganic carbonate, which is CO2, goes to the sediment, and then acidity through respiration, it then disappears. Also may not be correct. In terms of the actual formation of CO2, that's a bit in debate. Black carbon, of course, is not included, which we just talked about, and calcareous. The thing to note in sediments, and geochemists note that even though the thing, when you get sulphate reduction in oxide conditions, the sediment can continue to produce CO2, irrespective of the stuff on the surface, buried through sulphate reduction, because it produces a lot of base. That's something else which is not considered. It's a continual source over the centuries, or whatever, how long it's been there, of carbon dioxide, but how important is this? So, to work out the actual rates of degradation over a century, it's very difficult. So, but traditionally, it's been a case of using long-term sediment incubations over 500 days or more, if you can actually hang on there over if your end of contract doesn't interrupt at the time, which has happened in this particular case. And you hope that in that bit of time you've got enough in the shape and form of the decay to work out what the rates in the model of rate degradation. And there's two basic models. One is a thing called a multi-G model, which shows that there's a recalcitrant fraction and there's a labile fraction, and they don't turn into each other. One goes quicker and the other one hangs around. And there's another one which is getting more popular by Jack Middleburg, where basically the rate constant, first order rate constant, actually changes over time. The whole thing matures and gets more recalcitrant as a mixture. And each one will give slightly different results, and as you can imagine, because two different particular forms and explanations on how things go. There's this Middleburg's model showing that it's being used as a universal global model. It's been found to be more or less on a straight line at all scales and in all circumstances. But it is a global model, and it's a bit difficult to translate global models to specific situations. So we have to measure it ourselves. And the consequences of this changing rates of decomposition, if should happen, is that when we're looking at variability down to the sediment core, each of the sediments has a different age. And so we have to basically move the actual loss to the age of the system to take into account of the natural variability to get an indication of what may happen in the future. Or that's another debate, whether the past can predict the future of itself. So, what do we got here? So, long-term to do it, 500 incubations. We calibrate and construct the model on a sediment geochronology at greater than decade scales. That's a very important component of it, because if we know the age of the system, then we can actually reconstruct the model. It's Middleburg's model by knowing the age and how that function changes. But of course, we must know if it's the same organic mix, otherwise that will confound the actual rate of degradation. And we also, it's important to know in that experiment other pools which might be affecting the result in terms of if organic carbon is linked to CO2 or decoupled. So the study was in Sabah, near Kota Kinabalu, in an estuary, and it's to the upper part of the estuary, as you can see in that particular area. We also did some geochronology to constrain our interpretation in a similar seagrass Enhalus bed in a separate branch. And what we did, this is just the incubation, that shows you more or less the sediment, the top and bottom is about the same mix. We corrected for the Swiss correction, And then if you do any diagenic correction, you'd find out that more or less the things will coalesce even more. But we don't know exactly how much diagenic correction. Whoa. So when we did the basic model, we used a sophisticated model which has no basic assumptions on rate of sequestration and sedimentation, and based on an inductive approach where we model the profile. This is a very good, robust model, not the standard ones which have a lot of assumptions in the whole thing. We also discovered there from a rare cyclone, which confirmed the whole thing in Cyclone Greg, produced a mangrove layer. We put it all together and we see the rates of sedimentation, different in the two systems for different reasons. One is an event, one is basically maybe a loss of the density of the seagrass, inability to capture any more system. And then finally we got the degradation. And we can see from this, over 500 days, that more or less the two rate constants are not the same. One is getting more recalcitrant over time. So really it is the Middleburg model, which is probably the most appropriate to attach the results to. So if we do then the calculation just based on a single, the two formulas individually, you see that about 74% and 79% remaining after 100 years. So it does lose a reasonable amount in your sequestration values. So if we do recalculate, we can see from the sedimentation rate and so forth, we have to readjust the sedimentation rate and the sequestration rate accordingly. There are other models as well, but you can overfit them, unfortunately, which may be more appropriate, but they give rather strange results. So you have to look at, be careful of overfitting in these things. The black carbon itself didn't change, which is nice. And the decay model, we then try to apply to, looking at the 20-year-old differences. But unfortunately, we didn't have much success because the solution is such that the slope of that curve was negative and not solvable. So we have yet to really work that one particularly out. On the other side of things, we have, when we looked at the carbonate, we find that we're actually getting carbonate formation. And so we then had to do correction for the CO2 we got from the soda line, and you can see that the organic component did not agree with the CO2. So it's decoupled. So what if you're looking at disappearance of organic carbon, it may not give you the results you want in sequestration. Reasons for that, CO2 deficit compared to the pool, maybe possibly methane production or a recalcitrant pool. Then we have a surplus. On the bottom, we have basically a CO2 surplus and probably methane to CO2. But the reason for that, we don't think it's a DOC pool because our CDOM values when calibrated were too small. They're in millimoles, not moles. But what we did see also, interesting, that the ammonia fell and then later rose. And this was more or less consistent with another thing we weren't surprised to see, anemox formation. So we're getting dark CO2 fixation over time in the sediments. The extent of this we have no idea, but if you're a reductionist, like Peter, then it may be something to take into account if you want to model such a system. What else? More or less, the reason why we don't get sulphate reduction is possibly because the sediments are extraordinarily acidic. Normally in marine sediments, there's enough sulphate around for that to be used in preference. However, acidic conditions such as these will inhibit, because of H2S is the major form, bacterial reduction. So it may allow methane formation to happen in these highly acidic dominated mangrove sediments. Most of the sediments are captured by the mangroves. So there's a lot of going on in these systems to investigate. So we really would like to have increased the amount of incubation time because we believe we might not have captured all the characteristics of the decay curve in the first place. And if you're a reductionist, dark CO2 fixed anemox, maybe you have to investigate a little bit more. CO2 may be continually released by carbonate formation and possible methane production to account in these systems. Ta-da!
I know.